Welcome to Arc Dev Labs. It's good to see you.
When you tap the app icon, it opens instantly. But that single tap coordinates a complex data response across a global network of servers. This system manages over 2 billion active users. Every day, those users upload more than 100 million photos and videos to the platform. To maintain service, the architecture must operate within strict parameters. It requires 5 nines of availability, meaning less than 5 minutes of downtime per year, and must deliver content with sub-200 millisecond latency. The load is intrinsically unbalanced. For every photo a user uploads, thousands of other users may view it. The system must process significantly more read requests than write requests. A monolithic architecture cannot handle this specific ratio because you cannot scale read and write functions independently when their demands are so disproportionate. Managing this asymmetry requires a decoupled infrastructure. We can see how this decoupling works by tracking the life cycle of a network request from a mobile client. First, DNS resolution routes the user's connection. If the user is requesting static assets, like image files, edge content delivery networks intercept the request. The CDN serves the photo directly from a local node, preventing that traffic from reaching the main backend. Dynamic requests, like fetching a personalized feed, bypass the CDN and hit Layer 7 load balancers. Here, the system performs SSL termination, stripping the encryption layer so internal servers don't spend cycles on cryptography. From the load balancer, traffic flows into the API gateway. This gateway acts as the central orchestrator, inspecting application layer data to determine exactly which microservice should handle the request. This outer skeleton serves as a filter. By the time a request reaches the internal servers, it has been decrypted and routed to the specific pod designed to execute that logic. Managing high-resolution photo uploads presents a specific challenge for the internal services. Using a synchronous upload pipeline would require the API to hold a thread open for the entire duration of a mobile network transfer. At this scale, slow transfers would rapidly exhaust the server's available connections. To prevent this, the API accepts the payload, dumps the raw file into object storage like Amazon S3, and immediately acknowledges the client. The API then severs the connection. Instead of processing the file, it publishes a task payload into a message queue, such as Kafka. Independent worker nodes monitor this queue, pulling task packets to perform the heavy compute, image compression, resizing, and filtering. Once the workers complete the processing, they push the optimized assets out to the global CDN network for future reads. Asynchronous message queues act as shock absorbers for the system. They isolate slow computing tasks to ensure they never bottleneck the primary web servers. Generating a personalized newsfeed for a user in under 200 milliseconds is a primary read challenge. For standard users, the system uses a fan-out-on-write model. When a user publishes a post, the system pushes it into their followers' cache lists. When a follower opens the app, their device fetches this pre-assembled list directly from memory. This logic changes for celebrity accounts with hundreds of millions of followers. Attempting a fan-out-on-write for a celebrity would require writing a single photo to 200 million follower caches, which would overwhelm the message queues and increase database latency. The system utilizes a fan-out-on-read hybrid for these accounts. Celebrity posts are left out of pre-computed lists. When a follower loads their feed, the system pulls their standard list, queries a celebrity node separately, and merges the results on the fly. Engineering for these conditions requires identifying the network weight of individual users and switching between push and pull models to maintain performance. At the persistence layer, a single relational database cannot contain the entire social graph. Instead, engineers use polyglot persistence, selecting database architectures based on the specific structure of the data. Relational databases like PostgreSQL store structured data, such as user metadata and account credentials, where data integrity is required. Wide column stores handle massive append-only data like comments, which fit into flexible rows. To scale, engineers use database sharding. The database is distributed across hundreds of independent servers based on user ID to balance the load. Sharding requires balancing the distribution. A cluster of highly active users on a single node can create a hotspot, increasing the load on one server relative to the fleet. Isolating data by function and geographical shard ensures that a hardware failure in one database only impacts a fraction of the network. Even with distribution, querying a physical disk is often too slow to meet the sub-200 millisecond latency requirement. An in-memory barrier, typically Redis, is placed between the application logic and the drives. This cache-aside pattern serves the majority of read requests directly from RAM. This introduces the thundering herd problem. If a popular cache node expires, thousands of queries may simultaneously hit the database, exceeding capacity. To mitigate this, the system bottlenecks incoming traffic, staggering queries while a single request rebuilds the cache. Ephemeral contents, like stories, introduces different storage constraints. Because stories use a 24-hour time to live, the system can utilize ring buffers and cheaper storage tiers. The architecture prioritizes sequential writes for these temporary files over permanent archival storage. Tailoring storage tiers to the data lifecycle demonstrates exactly how engineers optimize hardware costs while maintaining high system speed. Evaluating the entire global system requires looking at how it behaves under network stress. The CAP theorem states that a distributed system can only guarantee 2 out of 3 traits: consistency, availability, and partition tolerance. Partition tolerance is a physical necessity in global networks, where connections will eventually be severed. The system must operate even when nodes cannot communicate. To maintain partition tolerance, engineers choose to prioritize availability over strict consistency. This results in eventual consistency. A user in Tokyo may see a different light count than a user in New York for several seconds until the databases synchronize across regions. Active-active load balancing across data centers ensures that if a regional facility goes offline, traffic reroutes to another continent with no disruption to the user. These engineering decisions reflect a trade-off. Users will tolerate a temporary discrepancy in a light count, but they will stop using an app that fails to load. Engineering at this scale relies on mastering these trade-offs to ensure that even during network partitions, the application remains available to the user.